Welcome back. So, last time we looked at process dynamics as a systematic way of characterizing the response of the output to a change in a causal input. We looked at basic response types, and we also looked at combination of the basic response types to represent any type of dynamic response. We also looked at a feedback control loop and sort of defined that, look, a control algorithm is something that takes in the deviation from the desired value in the output and converts that deviation to an equivalent control action or to an equivalent change in the input or the manipulated variable, so that the deviating variable is brought back to its target value. So, this is where we left ourselves last time, a feedback loop with its block diagram. Now, the most popular control algorithm which is implemented in what is here the controller in this guy, which is implemented in this controller, is called the PID control algorithm, and the P, I and D stand for proportional, integral and derivative. Okay. So, this PID control algorithm is the most commonly used control algorithm in industry, and this is even 90% of the controllers used in industry would be of the PID type, in fact of the PI type, and this is even as fancy model predictive controllers, advanced controllers have come into being, but the PID controller is still holding strong because we will go into it. A PID control algorithm. So, I think I will probably do this. So, you have the output from the controller, which is u, which is a function of time. You also have the error, which is the desired value, which is y set point, minus where you are right now. Okay. So, the error in the process variable or the controlled variable, you have that signal, and you would like to control this error into an equivalent motion, into an equivalent controller output or controller output signal. So, the PID control algorithm is ut is equal to a controller gain Kc times current error. So, ut is proportional to the error Kc times Et. So, this is called proportional action, plus 1 over tau I times integral of Et dt, this is called integral action, plus tau d det dE by dt, and we would like to close the bracket here. Again, please forgive my handwriting, it is lousy and I do not see any scope of it improving. Okay. So, this is proportional action, this is integral action, and this is derivative action, hence the acronym PID controller. Okay. Now, if I just a second, there is also a bias term here plus a bias term. This bias term is there so that the output of the controller is whatever the valve position is at that point in time at steady state. Okay. This bias term is there. It's easier to understand things if you use this is called the position form. The velocity form is, if you differentiate this equation, ut is equal to Kc times E plus 1 by tau I times integral of E dt plus tau d times dE by dt plus a bias term. If you consider a system at rest, why do you have the bias? I wanted to explain that. If you consider the system at rest, if the system is at rest, that means E is 0, everything is 0. So, if you have, so this term would at rest, the term in the bracket will go to 0. If you do not have the bias term, ut would be 0. What that means is the valve is either fully closed or fully open, depending on how you have defined it, but typically at rest the valve will be about 50% open. Okay. So, to ensure that there is no discrepancy, you will have to have this bias term to ensure that when the system is at rest, the equation holds. Okay. If you differentiate this equation, what you will get is du by dt is equal to, bias is a constant, that will go away, we will get Kc times dE by dt plus 1 by tau I differential of an integral. So, that will disappear, E plus tau d times d2E by dt square, second derivative of the error. This is what you will get. This is, so this is the first equation is called the position form of the PID algorithm, position form, and after differentiating the equation that you get after differentiating the position form, what you get is called the velocity form of the PID algorithm. Now, this velocity form is actually quite instructive. The error became non-zero because of a disturbance. Now, because the error is non-zero, controller will take some action, and finally let us say the process settles to, after disturbance, to some steady state. Well, at that final steady state, because by definition of steady state all time derivatives will go to 0. So, at that final steady state, what you will have is du by dt is 0. So, that will be 0, dE by dt must also be 0. So, that is 0. We do not know what the error is. So, I will just keep it at E at final steady state, okay, plus second derivative of time, because by definition of steady state all time derivatives are 0, we will get this. So, what you get is 0 equal to Kc by tau I times E final. For this equation to hold, for 0 to remain equal to 0, for left hand side is 0, right hand side should also be 0. For right hand side to be 0, this implies for the equation to hold, E final must be equal to 0. What does this mean? This means that if you have this error term, E final term came because your controller had integral action in there. So, what it means is, if you have integral action in your controller, then at the final steady state, error, that means deviation in the output, will be 0. Deviation in the output from its set point will be 0. So, essentially what it means is, integral action, the purpose of integral action is to ensure that there is always 0 offset at the final steady state. It removes offset. So, the purpose of integral action, what this analysis is showing is that integral action actually results in 0 offset. What is the purpose of the P and the D action? Well, we're going to see that in the presentation. Of course, yeah, these are the, so a P controller is nothing but only the P action. PI controller has got the P action as well as the integral action. The PID controller has got everything, the P action, the integral action and the derivative action. These constants Kc, tau I and tau d, these are called actually tuning constants. Kc, tau I and tau d, these are tuning constants. These are constants that are there in the hands of the designer to get the desired control response, okay, to get desired control performance. So, tuning constants. So, these are parameters that the control designer adjusts to get the type of response or to get the type of control performance that he or she desires. So, again I talked about the position form and the velocity form. The tuning parameters are the controller gain, the reset time, tau I is also known as sometimes reset time, and the derivative time tau d. Now, what is the purpose? I just explained to you that integral action actually results in 0 offset. Well, the purpose of P action or the proportional action, if you look at the position form or rather the velocity form, rate of change of controller output is proportional to rate of change of error. Okay. So, if the Kc is larger, for a small rate of change of error, you will have a large rate of change of or a larger rate of change of controller output. So, because you are changing the controller output at a faster rate, hopefully your speed of response would be faster. Okay. Your deviating variable would be brought back close to its set point faster. So, the purpose of P action is speed of response. Purpose of I action, like I explained, is 0 offset. What it essentially means is, if the error is non-zero, integral action will continue to move the U, the controller output will keep on adjusting the controller output until the error is driven to 0. So, because of this, integral action essentially introduces a seeking behavior. You keep on adjusting U until the error is driven to 0. So, this seeking behavior actually, if you go into control theory, it actually results in some amount of destabilization. D action is actually the opposite of I action. It brings in some amount of anticipation into the system, and because of the anticipate rate of change, which way am I headed, because of this anticipation, D action is sometimes used where you want a really fast and snappy response. The PI response is not good enough, so you introduce D action so that you can use a higher gain to get a fast and snappy response that is acceptable. So, this very common example here will be controlling a reactor temperature. Tight control of the reactor temperature is very desirable, because if it is a highly exothermic system, small deviations in reaction temperature can actually result in a thermal runaway. So, you want the temperature to be controlled really tightly. If you are using only a PI controller, that is not possible. If you bring in D action, then you can use larger gains in the P action. Larger Kcs can be used, and with larger Kcs you will get a faster and snappier response. Okay. So, D action is typically used to suppress oscillations because of the anticipatory nature, and because the I action causes oscillations because you are seeking. These oscillations get suppressed because of D action, and because the D action is suppressing oscillations, now you can use a higher gain Kc, okay, and this higher gain causes a faster and snappier response. Disadvantage of D action, well, if you take a signal and differentiate it, let us say I take a sine wave, I differentiate it, I will get I will get a signal which is like this. So, the D action actually amplifies noise. Okay. If you take the derivative of a noisy signal, the differentiated signal will be much more noisier. Okay. So, D action actually, derivative action actually causes noise amplification, and therefore, it is seldom used. It is only used where it is absolutely essential, and I just gave you an example, tight reactor temperature control. Because there is noise amplification in D action, typically when you are using a PID controller with the D action on, what you would have is the process signal that is coming, the signal from the sensor, it would typically be filtered to filter out the noise. Okay. How do you tune controllers? Well, two things. Okay, I think it is better explained in this figure. So, let us say you got a first order plus dead time process. You are feeding back the output Y, getting the error signal, and let us say you are just putting it through a P only controller, which is just multiplying the error with a gain K. Okay, and this is the output of the controller, which is the input to your first order plus dead time process. Okay. Now, let us say I give a step change to Y set point. What I am saying is, at time t equal to 0, what I am doing is Y set point goes up as a step. Okay. What I have done in this figure that is there is I have changed the gain, this value of K, from low to high values and seen what happens to the response as a step change in the set point is given. All right. At K equal to 1, the response looks like this. Okay. You want to get to 1, but because it is a P only controller, you go in that direction, but some offset remains. the output does not reach the set point. It goes towards the new value of set point, but it does not reach there. You increase the gain from from 1 to 3, well, output goes and the rate of change in the output is faster than with k equal to 1, but again some amount of offset remains. You increase the gain to 10, well, rate of change of output is much faster and now you start getting oscillations. However, some amount of offset still remains. If you increase the gain further to about, how much is it, to 16.35, okay, about 16, what you get is the rate of change is fast. However, the oscillations now are sustained, the oscillations do not die down. Okay. If you increase the gain further from say 16 to 17, what happens is these oscillations actually start to blow up. Okay. So, what I am seeing here is, as I am increasing the controller gain, okay, for a step change in the set point, at low controller gains I got a stable response, in the sense that my output moved from wherever it was towards the new set point. Of course, some offset remained. As I kept on increasing the gain, the offset reduced. As I further increased the gain, I started getting oscillations, then I reached the verge of instability, and if I increase the gain further, I got an unstable response. My closed loop system became unstable. So, first lesson is feedback control can actually destabilize your system. If the gain is too high, you will get a unstable closed loop system. Okay. So, now if you want to choose, so how do you choose a value of Kc? Well, a rule of thumb method would be, find out at what gain you start getting sustained oscillations. The implemented gain should be about half of that, okay, so that you are always away from instability, because you do not want an unstable closed loop system. So, the hit and trial tuning method is, find the controller gain at the verge of instability where you get sustained oscillations in the output. The implemented controller gain should be about half of that. So, this is the hit and trial tuning method. Okay. That value of the controller gain where you get sustained oscillations, which for this example in the figure is 16.35, is referred to as the ultimate gain. Okay. The period of the oscillations is referred to as the ultimate period. Now, based on the ultimate gain and the ultimate period of oscillations, Ziegler-Nichols and Tyrrell-Leibniz, and there are various other Cohen-Kuhn, there are various other empirical tuning procedures that use this value of the ultimate gain and the ultimate period to suggest what your controller tuning should be. So, the two most popular ones are Ziegler-Nichols tuning, and Ziegler-Nichols tuning is quite aggressive, and what is very many a times used for distillation columns, Tyrrell-Leibniz tuning. Okay. Now, maybe I should explain this a little bit. Okay. Look at the table. If you are using a P only controller, the Ziegler-Nichols tuning method is saying, get your ultimate gain where you get sustained oscillations, your applied controller gain should be half of that, Ku by 2. If you are using a PI controller, your proportional gain should be Ku by 2.2. What that means is, in a PI controller, I am supposed to use a gain that is slightly lesser than a P only controller. Why is the gain slightly lesser? Because integral action actually introduces that seeking behavior. So, what that means is, because of integral action, your response will become oscillatory at a lower gain compared to if you had no integral action. Okay. Now, if you introduce derivative action, notice that the controller gain is Ku by 1.7, which is higher than actually if it was a P only controller. What this is saying is, if you have introduced derivative action, you can actually use a higher gain, and the higher the proportional gain, the faster the response, the tighter the control. Okay. So, of course, PID, like I explained earlier, is used, and it is used when you desire a fast, tight and snappy response. Most common controller, PI. Okay. Where do you use P controllers? You use P controllers where you really do not care about offset. A very common example is level. In a tank which is just a surge drum, you really do not care whether the level is 50%, 55% or 45% or 60% or 40%, as long as the level is between 25 and 75%, you are okay. So, for this type of a system where the level is allowed to float in a range, offset is acceptable. Because offset is acceptable, the simplest controller that will give you reasonable control performance is a P controller. Simplest is best, therefore, level is typically controlled using P controllers. Okay. Tyrus-Leibin tuning, it is more conservative. You will find that the gain implemented in Tyrus-Leibin is actually significantly less than what is recommended by Ziegler-Nichols. And Tyrus-Leibin is typically applied to distillation columns because you do not want very large and sudden changes, aggressive changes in, for example, the reboiler duty, because that can lead to hydraulic problems. Okay. So, Tyrus-Leibin is more conservative tuning method, Ziegler-Nichols is for aggressive tuning, and the only point that I wanted to make here was that because of derivative action, you actually can use much higher gains, and therefore, PID controllers are used where you want tight, fast, snappy control of the output. Okay. If it is an electrical system, you have got an oscilloscope, you keep on cranking up the gain where you get sustained oscillation, you say okay, this is my ultimate gain, back off by half. In a chemical system where you are dealing with hazardous chemicals, you do not have that liberty of driving the process towards instability, because should something go wrong, well, you have got a disaster on your hands. So, because obtaining the ultimate gain and period of a control loop by increasing the control gain causes the process to be driven towards instability, you really do not have the liberty of getting the ultimate gain by the method that I just talked about, cranking up the gain till you get sustained oscillations. That cannot be done in a chemical process. So, therefore, alternative methods are needed which can be used for proper tuning of our PID controllers. Okay. These methods, two common ones are the process reaction curve method and the relay feedback auto tuning method, and we are just going to go over these two methods in the next few slides. Now, the process reaction curve method essentially tries to fit a first order plus dead time model to a S-shaped to an S-shaped output response. Okay. Most of the chemical process responses can be represented by a first order plus dead time model. So, what you do here is, so we have got this process reaction curve method, and in the process reaction curve method what you do is, your loop is opened, that means the controller is not on, you give a step change to the input, and here is the step change. Okay. In response to that step change, you record the output response, and this is the output response that you have, this line over here. Okay. Now, you take this output response curve, find out where the find out the inflection point in your S-shaped curve, draw a tangent at the inflection point. So, this is the inflection point and you have drawn a tangent at that inflection point. This tangent intersects the time axis here, then what you say is, this is my dead time theta. This tangent line is extended, and wherever it reaches the final steady state value, which is Kp, which is the gain of the process for a unit step, you note that time, and then what you say is, whatever that time may be, it is equal to theta plus tau p. So, you know theta from here, and then you say theta plus tau p is equal to this guy. Okay. So, then what you will say is that my first order plus dead time model is Kp comes from the final steady state value. So, Kp e to the power minus theta s divided by tau s plus 1. This is my first order model that I have fitted, and what you will see is, if you do this for this example process, the predicted model actually is much more sluggish than the actual process reaction curve, and that is considered fine, because for a more sluggish model where the model says that the process is responding slower, your gain that you get would be more conservative. So, you would be using lower gains. So, this process reaction curve method actually gives you a very conservative estimate of your ultimate gain, ultimate period. What I am saying is, you get the model based on the process reaction curve method. For that model, you obtain the ultimate gain or ultimate period using either a simulation or using complex algebra, which is very well covered in process control textbooks. From that ultimate gain and ultimate period, you apply Ziegler-Nichols or Tyrrell-Sleiban tuning and get your tuning parameters. Okay. The point why it is done is because the way the process reaction curve method works, it gives you tau that is larger than what the actual tau is, okay, and therefore your tuning is more conservative. Okay. That is about it. Note that in this tuning method, the control loop has to be switched off. You do a step test, then you can switch on your control loop back, and from the step test data you get your ultimate, you fit the model, get your ultimate gain, ultimate period, apply a tuning procedure, Ziegler-Nichols, Cohen-Kuhn, Tyrrell-Sleiban, and you get estimates for your controller tuning parameters Kc, tau I, tau d. Implement those, and then you may have to fine tune them a little bit further to get the kind of response that you want. Okay. There is also what is called the auto tuning or relay feedback method. What is done here is, your feedback loop is on, instead of the controller what you do is put in a relay. What does the relay do? The relay takes in this error signal, and if this error signal shows a 0 crossing, the output of the relay toggles to either, let us say, plus 5%. At the next 0 crossing of the error, the output will toggle to, let us say, minus 5%. So, plus h or minus h. Okay. I have just used as an example 5%. If you put in a relay in a feedback loop system, this is what happens, and that is shown in the figure. What happens is, the output toggles, the error crosses 0, and as the error crosses 0, your state of the relay goes from here to here. In response to that, the error crosses 0 again, toggles down, starts to go up, because the output has toggled down, it starts to go back down, crosses 0 again. Now, the output of the relay toggles back up. Now, the output which was going down, because the input has toggled back up, turns around, comes back, crosses 0 again. You see, it results in sustained oscillations with toggling of the input to the process. Okay. The period of these sustained oscillations is considered as equal to ultimate period, and from the amplitude of the oscillations in the output and the height of the pulse, plus 5%, minus 5%, plus 10%, minus 10%, that is something that you implement. So, from this you obtain Ku as this guy. The ultimate gain is estimated as 4 times the height of the pulse, the height of the relay toggling, divided by amplitude of the oscillations in the output divided by pi. This is how you estimate Ku. Note that in this auto tuning relay feedback method, your process, the feedback is on, a limit cycle is introduced, limit cycle meaning sustained oscillations. Note that the feedback loop is on and your process is oscillating around its steady state. So, this method is actually very popular, because this essentially ensures that you do not switch off the loop, you just put in a relay from the period of the sustained oscillations as well as amplitude of the output oscillations. You can estimate Ku, and then you apply an empirical tuning rule to get Kc, tau I and tau d. Advantages of this auto tuning method: those of you who have done some control theory, you would know that there is what is known as the crossover frequency, which is where the phase lag becomes the frequency at which the phase lag becomes 180 degrees. All right. So, this method actually results in those sustained oscillations which, and the frequency of that sustained oscillations is close to the crossover frequency. Large deviations away from the steady state are avoided, that is because your process is always oscillating around its steady state. The amplitude is obtained at the critical frequency, and that is what is important, so that this identification procedure is more accurate than step or pulse test, because the pulse test and step test have got more of lower frequency content. What you are interested in is the amplitude ratio at the critical crossover frequency. So, this ATV method actually causes sustained oscillations near the critical frequency, and the amplitude that you are getting in the output is actually closer to the amplitude ratio. Okay. Like I said before, once you have an estimate of Ku and Pu, you can either use Ziegler-Nichols, Tyrus-Levin, and there is also another one called Cohen-Kuhn settings to calculate your tuning parameters. Okay. Now we are going to talk about controller modes. Okay. Any controller, it's got 4 modes, and these 4 modes are indicator, manual, automatic and cascade. What happens in an indicator mode is no control action is being taken. It is, the controller is simply indicating what your process variable is. You cannot even adjust a valve position. Okay. In manual mode, controller is off, value of the process variable that is to be controlled is being indicated. However, since the controller is off, valve is at whatever position it is, the operator can change that valve position. He can say that the valve is 50% open, 60% open or 40% open. So, in manual mode, the operator is specifying the valve position signal, okay, the signal to the valve. In automatic mode, the controller is switched on, and now the position of the valve is governed by what should be the position of the valve is calculated by the controller, because the controller is on. What does the operator do? The operator specifies what should be the set point of the output. So, in manual mode, operator specifies the valve position. In automatic mode, operator specifies the set point of the output. There is also what is known as the cascade mode, and what happens in the cascade mode is even this set point is coming from another controller. Okay. So, these are the 4 modes of a controller. Controllers can also be reverse acting or direct acting, and what that means I will just explain in a little bit. Okay, it is not explained there. Reverse action and direct action, maybe that should be the last one that we do this time around. So, the controller can be direct acting or it could be reverse acting. What does it mean? Well, let me explain it. It is best explained plain English. Direct acting is, if my output that is to be controlled is increasing, I should open the valve, I should increase the output of the controller, that is direct action. What is reverse acting? If the output is increasing beyond the set point, I should actually close the valve, I should actually decrease my valve position. Just to explain it, for example, if I have a tank and I am controlling the level of that tank this way, and there is some feed that is coming, and this is under flow control. Let us say this is what I have. Okay. Let us say the flow to the tank increases. That means, if the flow increases, level would start to build up. If the level starts to build up, what should the controller do to the output valve? This output valve should be opened. What that means is, if at the beginning this valve is 50% open, the output from the level controller should increase from 50% in order to bring the level back, right. So, if the level is increasing, the output of the controller should increase. This is direct action. Okay. If you take the reverse situation, and let me explain this here, what you have here is, Well, the flow controller is here and the level controller is now on the feed. They are controlling the level this way. Okay. Now, if the set point here is increased, the flow out would increase, level would start to decrease. Now, in order to bring this level up back up, what should I do to the inflow? Since the level is decreasing, in order to bring the level back up, I must increase the inflow. What that means is, if this valve is initially 50% open, this valve should be opened beyond 50% to maybe 60, 65, 70% in order to bring the level back. So, what we are saying here is, if the level is increasing, controller output should be decreasing. Alternatively, if the level is decreasing, controller output should be increasing. This is called reverse action. Okay. So, we have just looked at the different modes of a controller: indicator, manual mode, automatic mode or cascade mode, and we have also just described the action of the controller, reverse or direct.